Here is a question that has launched 1,000 headlines. Is there life on Europa? It is a genuine question. It is worth asking. And the $5 billion spacecraft currently en route to answer it is not designed to answer it. Europa Clipper carries 9 instruments. Not one of them can detect life. That is not a flaw. That is the mission design. And the distance between what the headlines promise and what the instruments can deliver is where the real science lives. Start with what we know. In the 1990s, the Galileo spacecraft orbited Jupiter for 8 years. Among everything it found, one discovery changed the trajectory of planetary science. Europa, a moon slightly smaller than Earth's moon, showed magnetic field variations that were consistent with one explanation: a global layer of electrically conductive fluid beneath the ice. Salt water, not a pocket, not a regional deposit. An ocean, likely in contact with a rocky seafloor, possibly 60 to 150 kilometers deep. Twice the volume of all Earth's oceans combined, trapped under an ice shell roughly 10 to 25 kilometers thick. Galileo also photographed Europa's surface. What it showed was not a dead, cratered world. It was a surface that looked broken and reassembled, covered in long linear fractures called lineae, some of them thousands of kilometers long, some reddish-brown, colored by what may be salts or sulfur compounds delivered from below. In January 2026, researchers published findings that salty, nutrient-rich surface ice on Europa may be dense enough to sink through the shell under its own weight, creating a mechanism for surface-ocean exchange that does not require cracks or plumes. If confirmed, it means the ice is not a sealed lid. It is a slow, two-way membrane. The number of impact craters was low, which meant the surface was young by geological standards. Something was resurfacing it. Something beneath the ice was active. Challenger was a system that ignored data it already had. Europa Clipper is a system built to collect data that does not yet exist. But the press releases have been written as if the answers are already known. ___, quote, __, 0, ___. That framing sells. It is also misleading. The mission has 3 formal objectives. First, characterize the ice shell and its interactions with the ocean below. Second, understand the composition and chemistry of the ocean. Third, characterize the geology of the surface. Notice what is missing. The word, quote, 1 does not appear in the mission objectives. What does appear is, quote, 2. And this is where the distinction matters. Habitability means conditions. Life detection means organisms, metabolic byproducts. Biosignatures. They are not the same question. Europa Clipper asks whether the house has plumbing and electricity. It does not open the door to check who lives inside. A future lander mission might do that, but that mission does not exist yet, and building it depends on what Clipper finds first. So what can the 9 instruments actually see? Start with the one that has the hardest job. Reason, the ice-penetrating radar, will send radio waves through Europa's ice shell. The shell is estimated to be 10 to 25 kilometers thick. That is a range, not a measurement, because nobody has measured it directly yet. That is one of the things Clipper is there to fix. Radar can map the internal structure of that ice, find pockets of liquid water closer to the surface, and measure the shell's thickness with enough resolution to test whether the ice is convecting, which would mean heat is moving upward from the ocean. Convecting ice behaves differently from static ice. It means the shell is alive, thermally speaking, and that material exchange between surface and ocean is at least possible. What radar cannot do is see through to the ocean floor. The signal attenuates with depth. At some point, the ice absorbs more energy than the radar can transmit, and the image goes dark. The instrument has 2 frequency bands to work with, each optimized for different depths and resolutions, but neither one can reach through 25 kilometers of warm, salty ice and come back clean. Below a certain depth, the ice wins. Then there is mass specs, the mass spectrometer. Europa has a thin atmosphere, barely there, generated by charged particles from Jupiter's magnetosphere slamming into the ice and sputtering molecules off the surface. Some of those molecules may originate from the ocean below. If ocean water reaches the surface through cracks or plumes, the molecules that escape carry chemical signatures of what they pass through on the way up. Mass specs will taste that atmosphere, molecule by molecule, and determine what is in it. Salts, organics, sulfur compounds. The instrument is sensitive enough to identify individual molecular species at concentrations of a few parts per billion. What it cannot do is distinguish between organic chemistry and biology. A molecule of amino acid floating in Europa's atmosphere could come from life. It could also come from hydrothermal chemistry at the ocean floor, or from cometary material embedded in the ice billions of years ago. The instrument sees the molecule. It does not see the origin. That distinction is not a limitation of this particular spectrometer. It is a limitation of chemistry itself. Amino acids do not carry return addresses. Try explaining to someone that a mission to an ocean moon is not looking for life. Hale has tried. The conversation does not go well. The expectation is so deeply embedded that even correcting it feels like a disappointment. But the correction is the point. The instruments are not limited because NASA failed. They are limited because the question quote, _3 requires a level of certainty that remote sensing from orbit physically cannot provide. You need a lander. You need a drill. You need a sample. Clipper is the reconnaissance mission that tells you where to land. The ice-penetrating radar passed its first real test in March 2025, when Clipper flew past Mars and the Reason instrument successfully detected subsurface structure beneath the Martian surface. That test could not have been done from Earth. It confirmed the instrument works in flight, against a real planetary body, with real signal attenuation and real noise. The engineering is sound. The science begins when the spacecraft reaches Jupiter in April 2030 and starts its 49 close flybys of Europa, some as low as 25 kilometers above the surface. 49 passes, not one continuous orbit. The reason is radiation. Jupiter has the most intense radiation belts in the solar system, and Europa sits deep inside them. An orbiter circling Europa would accumulate a lethal dose of radiation for its electronics within weeks. Clipper's solution is elegant and brutal. An elliptical orbit around Jupiter that dips in close to Europa, collects data with all 9 instruments running simultaneously for a few hours, then retreats to a safer distance where the radiation drops by orders of magnitude. Each flyby is a sprint. The cumulative data set across 49 sprints will be the most detailed portrait of any ocean world ever assembled. There is a second layer to this that connects Europa to something closer: tidal heating. Europa's ocean stays liquid because Jupiter's gravity flexes the Moon's interior, generating friction and heat. The same mechanism that makes Io the most volcanically active body in the solar system keeps Europa's ocean from freezing solid. It is the same physics, the same equations, the same orbital resonance with Ganymede that drives the whole system. Different outcomes. Io bleeds lava onto its surface because it has no insulating ice layer. Europa traps heat under kilometers of ice and may channel it through hydrothermal vents on the ocean floor. If those vents exist, and if they carry the right chemistry, they would be the closest known analog to the environments on Earth where life exists without sunlight. Deep-sea hydrothermal vents on the mid-ocean ridges where bacteria and archaea build entire ecosystems on chemical energy from the planet's interior. No photosynthesis, no sun, just heat, water, and the right molecules. The parallel is why Europa matters to biologists, not just planetary scientists. Not because we know life is there, because the recipe is familiar. And because the recipe works in the one place we can check. ETHEMIS, the thermal emission imaging system, will map surface temperature variations. Hotspots could indicate thinner ice or recent geological activity, which could indicate regions where ocean material has reached the surface. EIS, the camera system, will photograph the surface at resolutions down to half a meter per pixel on some passes, enough to identify individual boulders and cracks. Europa, UVS, the ultraviolet spectrograph, will search for plumes, water vapor eruptions, similar to what Hubble tentatively detected in 2012 and 2016. If plumes exist and Clipper flies through one, mass specs and SUDA, the dust analyzer, could sample material directly from the ocean without landing. That quote 4 carries a lot of weight. Plume detections from Hubble were marginal, at the edge of the telescope's sensitivity. Some researchers are confident they are real. Others point out that the signal was never repeated reliably and that the statistical significance was borderline. Clipper will settle this. If Europa is actively venting ocean material into space, the mission changes from difficult to extraordinary. A plume fly-through would give us ocean chemistry without drilling through kilometers of ice. Mass specs could identify individual molecular species in the plume material, while SUDA catches and analyzes dust grains carried up from below. It would be as close to sampling the ocean as you can get without landing. But even without plumes, the dataset from 49 passes will answer questions that have been open since Galileo. How thick is the ice? Does it vary by region? Is the ocean truly global, or could there be isolated reservoirs? What is the salt content, and does it match the chemistry needed for the kind of reactions that sustain life on Earth? Is there communication between the surface and the ocean, and if so, where and how often? Are there organic molecules in the surface ice? Each answer narrows the field for what comes next. Each answer also raises new questions, which is how science is supposed to work, even though headlines prefer answers that close the loop. The gap between the headline and the mission is not a failure of ambition. It is a measure of honesty about what orbital reconnaissance can do. Europa Clipper will not find life. It will tell us whether the conditions for life exist, how those conditions vary across the Moon, and precisely where to send the next mission. That distinction sounds small until you realize that every dollar of the next mission depends on it. The lander gets built or it does not, based on what Clipper brings back. There was a Europa lander concept. NASA studied it. It would have drilled into the ice, analyzed samples on the surface, and looked for biosignatures directly. The estimated cost was north of $2 billion on top of Clipper's 5. Congress asked questions. The concept was shelved, not canceled, pending Clipper's results. If Clipper finds the right combination of thin ice, active geology, and organic-rich surface deposits in the same location, the lander argument becomes much easier to make. If the ice is uniformly thick, the surface uniformly dead, and the chemistry uniformly ambiguous, the argument gets harder. Clipper is not just a science mission, it is a decision point. And that is perhaps the harder question. Not whether life exists on Europa, but whether an answer that says, conditions are favorable, send a lander, will carry enough weight to survive a budget cycle. Europa Clipper asks a question the instruments can answer. The question after that one belongs to a budget committee. And budget committees, unlike ice-penetrating radar, do not operate on the frequency of curiosity.